Dear students, welcome to the session on Hagen-Poiseullie flow, otherwise called as laminar flow, also called as viscous flow. And this type of flow we can experience only, or we should experience only in a fully developed region. Okay, so for example, when a flow is going to happen through a pipe, initially when the velocity vectors will be like this. Okay, but the flow will try to develop and hence the velocity vectors will come like this, and finally it will reach a shape of a parabola. Okay, so this is the region where the flow is trying to develop. So this region is called as hydrodynamic boundary layer length. Okay, or the region is trying to, this region is the region where the flow is trying to develop. And beyond this one, it is called as what? Your fully developed flow. Okay, so this is called as what? Fully developed flow. So this is the hydrodynamic layer length where the flow is trying to develop on its own from this region to here. So whenever we are going to study about this Hagen-Poiseullie flow, it's not concerned about this region. It concerned about this particular domain. After the flow is fully developed or fully developed flow, there only we are going to study the flows. Then it's called as what? Hagen-Poiseullie flow. Okay, as well as this flow will not contribute to the turbulence characteristics. Why means we know that Reynolds number is nothing but a ratio of inertial force to the viscous force. So here the viscosity effect will be very high. When the viscosity effect is very high means, or we are calling this as viscous flow, which means the effect of mu is more predominant, or we are considering a real fluid where we can't avoid the viscous nature of the fluid, as well as the viscous force dominates the inertial force, which means the denominator is very, very high compared to the numerator. So the value of the Reynolds number will become less. The value of the Reynolds number will become less, and if this value is going to be less than 2000 for the flow is happening through a pipe, then the flow can be considered to be what? Laminar flow. Okay, so in our case also, since the denominator is very high, since it's viscous flow, the numerator will become less, and suitably it should be very less than 2000 for the flow to happen as laminar inside a pipe. So the flow is also called as either laminar flow or viscous flow. Now what is the objective of studying this Hagen-Poiseullie flow is to determine how much of head loss may be there, or how much of pressure head loss will be there because of the viscosity of the fluid. That is the main intention of the Hagen-Poiseullie flow. I will repeat once again. The main intention of studying the Hagen-Poiseullie flow is to know how much amount of head will be lost because of the viscous nature of the fluid. That is the main purpose of the Hagen-Poiseullie flow. Okay. For this, now let us consider the flow which is going to happen from from left to right, from say inlet to exit. Let us say it is 1 dash. Let us try to go up to 2 dash. So when the fluid is trying to go from 1 dash to 2 dash, there is a loss of pressure head, or the pressure when it's trying to travel from 1 to 1 because of what? The viscous nature of the fluid. So that only we are going to study. Okay, that is our intention. So once again I'll repeat, the flow should be studied only in the fully developed domain, as well as when the Reynolds number, it should be viscous flow, or the viscosity is very high, so the Reynolds number is very less, such that the flow will happen in the laminar region. The flow will happen in the laminar region. So these are the three keywords already we have discussed. Now this is the pipe through which the fluid is going to enter from here and going to leave here. And you may be wondering what we have drawn here as ABCD. ABCD is nothing but I am going to consider a cylindrical element through this pipe, through which the flow is enter across AB and going to leave along CD. I will repeat once again. This ABCD is not real. It's an imaginary cylinder element we are considering on our own to study the flow physics happening is going to enter through AB and going to leave along CD, which is going to enter along AB and going to leave along CD. Now what will be the pressure force at AB? So what will be the force at AB and what will be the force at CD? Okay, now the force at AB will be the pressure force. So we know that pressure equal to force by area. So the pressure force at 1, 1 or at AB. Let us call the 1, 1 plane also lying exactly at AB, not here and here. Let's consider between the fluid element. So let us, the 1, 1 plane is now at AB. So now the pressure force at AB will be equal to P1 into A. So this is the pressure force at AB, P1 into A. So what is the area? Is nothing but the area of the circular domain. So it is nothing but P1 into pi r squared. If you want, you can put pi d squared by 4 also. But we are telling us what? The cross-sectional area of this cylinder element will be pi r squared. So this is the force which is available at the inlet to the cylindrical element AB. So by means of Taylor series, already we know that what will be the force which will be available at CD. Please refer to my Euler's equation, Reynolds equation and other substantial derivative to understand how we are going to get the value at CD by means of Taylor series. Okay, if you know the value at AB, we can find the value at CD by means of Taylor series using the formula f of x plus delta x will be equal to f of x plus dou f by dou x into delta x by 1 factorial plus higher order terms. So here f of x plus delta x is nothing but the pressure which we want to know at CD. Okay, what is f of x? The pressure at the AB. The pressure is the pressure force at the AB plus dou f by dou x into delta x. Here delta x is nothing but the length of the element. When I want to apply this formula, this delta x should be very, very small. This delta x should be very, very small. Let us continue further. If I want to know the force at the plane CD, which is nothing but the pressure force at CD is given by the pressure force at AB, which is nothing but P into pi r squared plus dou by dou x of, what is the function here? The pressure is the function into delta x into what? Into pi r squared. Into pi r squared. So what is the common thing between these two terms? It is nothing but P plus dou P by dou x into delta x of pi r squared. So now if we consider the force, pressure force which is available at AB as P into pi r squared, I will repeat once again. Instead of P1 I put only P now, because if I know the pressure force at AB as P into pi r squared, the pressure force at CD will be given as P plus dou P by dou x into delta x of pi r squared using the Taylor series. You please refer my earlier videos on Euler's equation, Reynolds equation and substantial derivative. How we got, here also we have explained the same. Okay, that's fine. So this sign will be negative. This sign, the pressure force which is available at CD will be negative, whereas the pressure force which is available at AB is positive. The reason is very simple. One, if I am going to consider the fluid element, through AB is going to enter. So whatever is the inflow, we are considering as positive, and whatever is the outflow, we are considering as negative. So I know now the pressure force at AB as P into pi r squared, pressure into area. Now I know the pressure force at CD as what? P plus dou P by dou x into delta x, where delta is the length of the cylindrical element, into pi r squared. The inflow is positive, the outflow is negative. So this is the another pressure force. So now we consider the two pressure force is acting at the inlet and at the outlet of the cylindrical element AB and CD respectively. There is also another force which makes the flow to restrain, or which will be an opposing force. That force is created by the shear force. That's what I have already indicated as tau. The shear force will act on the periphery of the cylindrical element. So what is the periphery? It is the perimeter. What is the perimeter? It is either pi d or 2 pi r. So this perimeter into this entire length. What is the entire length? It is nothing but delta x. So there is another force which is acting on the fluid element along its periphery, which will oppose the motion from inlet to outlet. It is like a resistance to the flow, but it's not because of friction, but it's because of the viscosity. Because we are dealing with the viscous flows. So now we want to know that force. So what is the force? It is nothing but shear stress. Shear stress is having a unit of what? Newton per meter squared. But I want only the force. So multiply by area. So what is the area? It is 2 pi r. Why is 2 pi r? It is nothing but the perimeter of this element. into the whole surface area, this area should come. So it is multiplied by the length. The length is nothing but what? Delta x. So now this is nothing but what? Shear stress is Newton per meter squared. This unit is what? Newton per meter squared into this area. This area is what? Meter squared. So when I am going to cancel out, it will become the shear force. It will become the shear force. So I will repeat now. We are having three forces. The one force is at the inlet, which is nothing but what? Pressure into area. I want to know the pressure force at CD, which is given by Taylor series as P plus dou P by dou x into delta x of pi r squared. So these are the two pressure forces. One more force is there, which is an opposing force to the motion, which is caused by the viscous nature, which is given by the shear stress between the fluid layers. So that is nothing but what? Shear stress into the corresponding area. What is that area? That area will be what? This circumferential area into the length. Circumference perimeter into the length will give me my area. So it's nothing but 2 pi r into delta x. Now we will try to equate. Now we will try to equate all these forces. So it is nothing but P into pi r squared minus P plus dou P by dou x into delta x of pi r squared minus, why I am putting minus? Because this shear force is also trying to oppose the motion. So tau into 2 pi r is nothing but the perimeter into the length is nothing but delta x is equal to 0. Is equal to 0. Because the steady state it remains, there's an equilibrium exists between the inflow and the outflow. Now from this, what are the common terms we can divide? We can divide pi. Before dividing, we will expand it. So P into pi r squared minus P into pi r squared minus P, not P, minus dou P by dou x into del x into pi r squared minus tau into 2 pi r into delta x equal to 0. So we can cancel out pi r squared into P minus P into pi r squared. So we are left with these two terms. Okay, so among these two terms we can cancel off delta x, we can cancel off 1 pi, 1 r. So now what is the resultant solution? It will be 2 minus 2 tau equal to dou P by dou x. Equal to what? Dou P by dou x into r. This r is also there. So dou P by dou x into r. So from this, what is tau? From this, tau will be equal to minus dou P by dou x into r by 2. So this is the relationship what we obtained by balancing the force which are acting on the cylindrical fluid element. So tau is nothing but the shear stress is equal to minus dou P by dou x into tau by into r by 2. R is nothing but the radius of the cylindrical element. Here the beauty is that dou P by dou x remains a constant. That is, for a particular pressure drop along the x-direction, the flow is happening. So dou P dou x remains constant. So we can see that tau is a function of the radius. Tau is a function of radius and it becomes equal to 0. The value of tau will become 0. When the tau will become 0? When r equal to 0, tau will also be equal to what? 0. So I can tell the value of tau I am plotting. The tau is nothing but what? Shear stress distribution. Tau is nothing but what? Shear stress. Now we are going to show how it is going to be distributed in this pipe layer. So it's called shear stress distribution. So when r equal to 0 means tau will also be equal to what? 0. Okay. When r equal to capital R, it will be maximum. When r equal to capital R, it will be maximum. So the lines will be like this. So this black color lines indicates it's a linear. It's varying linearly. It's varying what? Linearly. So the line is like this. The line is like this. So we can see the shear stress is maximum at the walls and becomes 0 at the center. So this black color profile indicates my shear stress distribution. Shear stress distribution. Let us continue further to get the velocity profiles. As well as the pressure drop. Equating equation 1 and 3, we get minus mu into du by dr is equal to minus dou P by dou x into r by 2. Just you written du alone here, the minus will become plus. So du will be equal to 1 by 2 mu into dou P by dou x into r. That's it. So du is this one. So just I written du, I have taken dr this side and I have taken this 2 and mu over the denominator. So du this one. Integrate on both sides. So now it will become u. That is when I'm going to integrate du, it will become u. So it will become 1 by 2 mu or dp by dx or dou p by dou x, okay, into r squared by 2. Because when I'm going to integrate r, it will become r squared by 2 plus constant of integration as c. Plus constant of integration as c. Now u is called as 1 by 4 mu dp by dx of r squared plus c. Now I want to find the value of constant of integration, namely c, by applying the boundary condition. So I hope I can erase it now. We got an expression for the velocity profile, which is given by u equal to 1 by 4 mu dp by dx into r squared plus c. But our objective is not to now to find what is the value of c. So you see, when the flow is going to happen, what are the velocity of the fluid at the walls? What is the velocity of the fluid at the walls? It will be 0. It will be 0. Why it is 0? Because of no slip boundary condition. What does it means by no slip boundary condition? It means the velocity of the fluid very close to the wall cannot pierce and it is assumed to be at rest. So which means when my small radius becomes capital radius, capital R, when my small radius becomes what? Capital R, my velocity will become 0. So please make a note, when R it becomes what? Capital R. That is of the walls. What will be velocity? Velocity will be 0. So I want to find the constant of integration. So try to substitute this boundary condition to find the value of c. Now when I am substituting this value, 0 will be equal to 1 by 4 mu of dp by dx of capital R squared plus c. Why small r become capital R? Because when small r becomes capital R, my velocity will be 0. My velocity will be 0. So from this, what is the value of c? C equal to minus 1 by 4 mu of dp by dx of r squared. So now we got the value of c. Let us call this as equation number 5 or 5. Let us call this as 4. Substitute 5 in 4. So substitute the value of c in this equation. We will further get it. We will further get some more solution. Okay. So instead of c, I can substitute this value now. So instead of this c, I am going to substitute as 1 by 4 mu. Why this minus sign came? Because it is there dp by dx of r squared. Generally it is advisable to have capital R squared as first term because capital R is bigger than the small r. So we can interchange this term. So the same expression can be written another way. U will be equal to minus 1 by 4 mu of dp by dx of r squared minus r squared. So now you see, I written the same only. I have taken 1 by 4 mu dp by dx as common term, but I put as minus sign outside, so that it will be r squared minus r squared. You multiply and see, it will be what? This term will be minus like this. This term will be positive like this. But why I have written like this? Because capital R is always greater than small r, so this term will be positive. This term will be positive. So u equal to minus 1 by 4 mu dp by dx of r squared minus r squared. This is the expression what we arrived for. Which one? The velocity profile. The velocity profile definitely depends upon what? The pressure gradient along the x-direction. That is the only force which drives the flow. Along with that, it has been constrained by the viscosity. It has been reduced because of the viscous nature, and also it will be the radius of this also will play a role, which means it's also is going to vary with respect to radius. So when the radius is going to be capital R, then my velocity will become 0, and the velocity will be maximum at the center. When the small r equal to 0, then I'll get the maximum velocity. So this equation is a wonderful equation which will try to give an explanation how the velocity profile will be happening inside a pipe. Okay, so this velocity profile will be happening because of the pressure gradient along the x-direction and inversely proportional to the viscosity. If the viscosity is more, then my velocity will be less. That's fine. Then coming to the radius, where the velocity will be higher, the velocity will be 0 at the walls. The velocity will be, because when r equal to capital R, the center u will become 0. And when this small r becomes 0, what? This will become u max. It will become what? U max. Otherwise, I will put as, when small r equal to 0, my u will become what? U max. Okay, so my u will become minus 1 by 4 mu of dp by dx of r squared. So this is nothing but my u max. This is nothing but what? My u max. What is u minimal? U minimal will be equal to 0. Why it will be 0? Because when r equal to capital R, when this r equal to capital R, it becomes 1. So this will become 0. The entire time will become 0. That is nothing but what? Our no slip boundary equation. So this is the profile for the velocity. So this equation takes the form of a parabola. This equation takes the form of a parabola. So my velocity profile will be like this. What is from this profile? What are you getting? The velocity at the walls are 0. As I told now, the velocity at the walls are 0 here and here. And the velocity will be maximum at the center when r equal to what? 0. So we can see a parabolic profile is obtained. This is what? Parabolic profile for the velocity. So we can consolidate now. I am getting a straight line relationship for the shear stress. I am getting a parabolic profile for a velocity, for the velocity. We will continue further to obtain the average velocity. Then we will try to compare with the maximum velocity and the average velocity. Finally also we will try to arrive at the pressure drop across this fluid element. Okay, we will continue further. In the last session, we were discussing about how to obtain the velocity profile, and we arrived this formula. U is given by minus 1 by 4 mu of dp by dx into capital R squared minus small r squared, where capital R is the radius of the pipe and small r is the radius of the cylindrical element. And we see that this velocity profile takes the form of a parabola, and it will be minimal at the walls because there it will become my small r will become capital R, and hence u will become 0 and u will become 0. So we can find the velocity at the walls is 0, and when the small r is equal to 0, I will get the maximum velocity given by u max. U max equal to minus 1 by 4 mu of dp by dx of capital R squared. So we can see the velocity is maximum at the center. So we are able to obtain u max and velocity profile, and the velocity profile seems to be parabola, whereas the stress distribution is linear given by this equation. It is a linear equation. Now let us try to explore further, and let us try to arrive at a condition where what will be the ratio of the u maximum to the u average. So our next step is to, already we have found u max. Now we have to find u average. Then we will try to divide u max and u average and try to find what is the ratio, and try to find what is the ratio. That is our next step. So let us erase this particular value of stresses. Already we have completed, and I will use this space for writing the u maximum value. So u max is nothing but given by minus 1 by 4 mu of dp by dx into r squared. So this is the formula for finding the maximum velocity, and this is the formula for finding the velocity profile. Okay. So now let us try to find the Q. Q is nothing but the discharge. Okay. Let us try to find the value of Q. What is Q? Q is generally given by area into velocity. Area into velocity. So what is, now what I am going to consider means, I am going to consider the flow which is going to happen through the small thickness. Now you can see there is a small thickness. This thickness is dr. Let us see, through the small thickness, some amount of fluid leaves, enters and leaves. Okay, I want to know the discharge through the small thickness dr. So then the formula will not be Q, it will be called as dq. So dq will be equal to, what is the area of this small thickness through which the fluid will pass through. So that the area will be equal to 2 pi r into dr. Why is 2 pi r? 2 pi r is nothing but the perimeter into the thickness will give me the area through which the fluid will enter and leaves the surface. So the area through which the fluid enters and leaves is nothing but 2 pi r into dr. This is the area. What about the velocity? The velocity is given from here. The velocity is given from here. Because the velocity remains same, whether it's going to be small area or a bigger area, so the velocity is the same. So I have to substitute the value of velocity over here. So I can write once again here the form of like this, minus 1 by 4 mu into dp by dx of capital R squared minus small r squared into my area. Area is 2 pi r dr. So this is not, now what is the formula? This is velocity into area or area into velocity. So we got q, but this q is not the complete q. It is only the q through the elemental ring element, namely of thickness dr. When continuing further to obtain the value of q, let us integrate. Let us integrate this equation. So if I want to have the total flow rate, so it will be, this is nothing but my dq. So my q will be equal to integral of minus 1 by 4 mu into dp by dx of r squared minus r squared into 2 pi r dr. What is the limit? The limit should vary from the center point to the outermost radius. This is the capital R. So the limit is from 0 to r. 0 to capital R. Now here the variable is only small r because capital R is a constant. So let us first multiply this term r with this one. So I hope I can multiply here itself. So it become r squared into small r. This term r squared into r will become r cube. So I hope you can understand. I'm going to take this r to inside. So it is r squared into r minus r cube. So this r I have taken inside. So it become r squared r minus r cube into 2 pi into dr. That's fine. Now let us integrate this term. Okay. So it will become, when I'm integrating it will become minus 1 by 4 mu is a constant. dp by dx is a constant. When I'm going to integrate it will become r squared. This r when I'm going to integrate it will become r squared by 2. This term will become r power 4 by 4 based on the integration into 2 pi into 2 pi. So the limit is from 0 to r. The limit is from 0 to r. So on working further, on expanding further, so we can see this r power 4 by 2. Okay. So this, I'm going to apply the upper limit minus lower limit. There's no need of applying the lower limit because it becomes 0. So I'm going to apply the upper limit. So it is minus 1 by 4 mu into dp by dx of r power 4 by 2 minus r power 4 by 4. How I got? Because this r is also capital R. So r squared into r squared become r power 4 by 2 minus r power 4 by 4 into 2 pi. So it will become, if I am going to take a LCM, it will be 4. It will be 2 r power 4 minus r power 4 into 2 pi. Isn't it? I hope you can understand. Okay, so it is 2 r power 4 minus r power 4 minus 1 by 4 mu of dp by dx. So whatever we are now trying to get is only q. Whatever we are trying to get is only now q. So it will become, if I am going to take, it will become what? I can cancel off this 2 with 4, so it will become 2. 4 into 2 is 8. So minus 1 by 8 mu of dp by dx into pi of 2 r power 4 minus r power 4 is nothing but r power 4. So this is the value of q. This is the value for the discharge. This is the discharge through the entire pipe radius of capital R. So we can see the q is given by minus 1 by 8 mu dp by dx into pi into r power 4. But our aim is not to find q. Our aim is to find the u average. So once again, how to find u average? So u average will be equal to q by a. Q by a. I hope you got it. So I will expand further. I am interested to find u average. So we know that q will be equal to u average into area. Now which is the area? This cross-sectional area or this entire area. So that area is nothing but what? It is nothing but pi r squared, which is nothing but the area of the circle. So this is the formula. Now I want u average only. So u average will be equal to what? Q by pi r squared. Which means I want to divide this area by pi r squared. Here the r is what? This r is the radius of the entire pipe. So it is capital R. It's nothing but what? Capital R. Got it what I'm telling? Why I replace small r with capital R means because the diameter radius of this entire pipe through which the flow is happening. So it is pi r squared. So now I can divide this value by pi r squared. So I can write like this: minus 1 by 8 mu dp by dx into pi r power 4 divided by pi r squared. So I can cancel off pi. I cancel off r squared. This r power 4 will become r power 2. So now the u average is given by minus 1 by 8 mu of dp by dx into r squared. So this is the value of u average. So already you have the formula for u maximum. So you can see both are almost same. The only thing is what? The denominator is 8, here the denominator is 4. So u maximum is twice as that of u average. U maximum is what? Twice as that of u average, because dp by dx is also there. R square is also there. The only difference is what? Here is 1 by 8, here is 1 by 4. So we will do that also, it's not an issue. So now our aim is to find u average by u maximum by u average. So u maximum by u average. So u maximum I am taking from here, minus 1 by 4 mu dp by dx into r squared, and here u average will be minus 1 by 8 mu into dp by dx whole r squared. So dp by dx cancel, r square cancel, minus minus cancel, mu cancel. So it become 8 by 4. 8 by 4 is nothing but 2. So we saw that the maximum velocity will be equal to twice of the average velocity. So that is the relationship what we obtained through this particular derivation. So is thus we see here that the u maximum is twice of that of the u average, or u maximum by u average will be equal to 2. U max by u average equal to 2. Let us now further explore to obtain the pressure drop when the flow is happening between section 1 and 2, when the fluid is having more viscosity, or when the flow is viscous flow. So that is the main formula behind this Hagen-Poiseullie flow. Let us come now to the final end of that one. Okay, for that I want to know the pressure value. That pressure can be obtained from the u average formula. Okay, I will proceed further to obtain the pressure drop between the section 1 and the 2. So this is also one of the outcome. What are the outcome? U max by u average is equal to 2. This is also one of the outcome. Now let us try to find delta P across the section 1 and 2. Okay, or between any two planes. Okay, fine. So for that we are going to make use of this equation. U equal to minus 1 by 8 mu of dp by dx into r squared. Here our aim is to find dp. So I will have this dp over here. It become 8 mu u into dx by r squared. I have taken this minus also this side. So from this u average, I am trying to find dp. I am trying to find the value of dp. So from this we got what is dp is this much. I have to now integrate on both sides to find the actual pressure difference. So it will become 1 to 2 dp is equal to minus 8 u mu by r squared into integral of dx. It is 1 to 2. It is 1 to 2. So this pressure will become what? P2 minus P1. P2 minus P1 is equal to minus 8 u mu of r squared. This dx will become what? X on substitute the limits will become what? X2 minus x1. So what is x2 minus x1? From here to here it is called as x2. From here to here it is called as what? My x1. So x2 minus x1 will be equal to delta x. This x2 minus x1 will be called as what? My delta x. So I can write it here further. So P2 minus P1 is equal to minus 8 u into mu by r squared into delta x. So I will multiply by minus on either side. So this will become P1 minus P2. This will become plus 8 u mu by r squared. Because P1 will be always greater than P2. We know that because the pressure is going to last into delta x. So I multiply by both sides by minus 1. That's fine. Now what is R in terms of D? 2R equal to D. So R equal to D by 2. Radius equal to diameter by 2. So substitute for R squared, it will become what? D squared by 4. So substitute for R squared is what? D squared by 4 here. So it will become P1 minus P2 into 8 u mu by d squared by 4 into delta x. Okay, it's very simple steps. Now this 4 will, when multiplied by 8, will become 32. So P1 minus P2 will be equal to 32 u mu, u is the velocity, by d squared into delta x, Generally, we are not only intended to find delta P, but also we are intended to find the pressure head, that is P1 minus P2 by rho g. So I want to divide both sides by hg, because already we know that by Reynolds equation, P1 minus P2 by rho g will be equal to the head loss. Okay, HF, head loss due to the friction and other effect. Here the viscosity dominates the other effects. Okay, so now we want to know what is the value of P1 minus P2. That will be your HF. Okay, so I'll divide this term also by rho g on either side. So it will become what? P1 minus P2 by rho g will be equal to 32 u mu by d squared into rho g of delta x. Now this is obtained from Reynolds equation. Let us keep some equation number. Let us say it's 8. Let us say it's 9. Why I am telling means, so since the left hand sides are equal, the right hand should also be equal, which means HF will be equal to 32 u mu by d squared rho g into delta x. This particular formula is known as Hagen-Poiseulles, Poisuille, apostrophe s formula. This formula, what you are able to understand, this formula is able to find the head loss through the pipe flow when the viscous effect dominates. How we know the viscous effect is there? Because mu is there in the numerator. And this head loss will become less when your diameter is very big. When the diameter is bigger, automatically this head loss will come down. And it will increase with the viscosity of the fluid. So if you have a viscosity of the fluid higher, then my head loss due to the viscous flow will also be higher. And this particular formula is known as Hagen-Poiseulles flow. So formula. And I hope now you will be able to enjoy and appreciate the loss of head in the pipe due to the viscous effect. And the corresponding loss of head is given by this particular formula, and it is known as what? Hagen-Poiseulles formula. So from this, what are the things we are getting? The 4 parameters whatever we are getting is nothing but the first thing what we got is the shear stress distribution, which is nothing but tau equal to minus dou p by dou x into r by 2. This is the first observation we got. This is the first outcome we got. The second outcome we got is u max equal to minus 1 by 4 dv by dx into r square. This is the second one. The third one is what? U max by u average equal to 2. And the fourth one is nothing but what? Head loss due to the viscous effect is given by 32 u mu by d square rho g into delta x. I hope you will be able to appreciate the content in this one and also the usage of the Hagen-Poiseulles flow. Especially this Hagen-Poiseulles flow is much needed for a viscous flow. For a viscous flow means where the mu dominates. Thank you.